The superposition principle enables us to combine known states of a quantum system to create new states. Its full potential, however, becomes apparent when it is applied in conjunction with special quantum states, known as stationary states. I will now define stationary states and tell you about the various interesting and useful properties. But before diving into the details, here is a broad overview. As the name suggests, a stationary state of a quantum system is one in which the system appears motionless. Stationary states have definite energies. Motion arises from the superposition of stationary states with different energies. Understanding all the stationary states of a system and the corresponding energies allows us to predict the system's time evolution in the most general scenario. I will now show you how stationary states appear in quantum mechanics. Consider a quantum particle with the wave function psi governed by the Schrödinger equation. H hat is the Hamiltonian, given by the sum of the kinetic energy operator, which involves the second derivative with respect to the particle's position, and the potential energy V. Let's try to find solutions to the Schrödinger equation in a special, separable form. Specifically, we'll look for wave functions psi, dependent on x and t, that can be written as a product of a function of x and a function of t. We'll denote the function of x by lowercase psi, and the function of t by phi. The reason for focusing on such separable solutions will become clear later. The left-hand side of the Schrödinger equation involves the time derivative of the wave function psi. For the separable states we are considering here, this time derivative equals the product of lowercase psi and the derivative of phi. In the right-hand side of the Schrödinger equation, we have the operator h hat applied to the wave function psi. Note that h hat only affects the spatial part of the wave function, lowercase psi, while the time-dependent part phi acts as a constant multiplier. Therefore, we can rewrite the right-hand side of the equation as h hat applied to lowercase psi, with the result multiplied by phi. Let's now divide both sides of the equation by the product of lowercase psi and phi. Then, we can cancel psi on the left-hand side of the equation, and phi on the right-hand side. In this way, we end up with the following equation, which represents the Schrödinger equation for separable states. To ensure clarity, I have explicitly indicated the time dependence of phi on the left-hand side and the space dependence of psi on the right-hand side of the equation. Now, observe the following crucial fact. The left-hand side of our equation is a function that depends solely on t, whereas in the right-hand side, we have a function that depends solely on x. It's important to note that we require this equality to hold for all values of x and t. Ask yourself the following question. How can two functions, being functions of different independent variables, be equal to each other for all values of the variables? The answer is this. The equality can hold for all x and t, only if the left-hand side is in fact independent of t, and the right-hand side is independent of x, and both sides are equal to the same constant, which we'll call e. Otherwise, by varying say t, one could change the value of the left-hand side without altering that of the right-hand side, thus causing the two values to no longer be equal. The fact that the left-hand side has to be a constant function gives rise to the following equation for phi. This is a simple first-order differential equation with constant coefficients, and as you can easily verify, its solution is this complex exponential function. In principle, we could multiply this exponential function by any arbitrary constant. However, such multiplication is unnecessary because we can incorporate this constant into the function lowercase psi, which will subsequently multiply phi. Now, let's focus on the right-hand side of the Schrödinger equation. The condition that it must equal the same constant e leads to this equation. Alternatively, by multiplying both sides by lowercase psi, we can express the equation like this. Or, by substituting the explicit form of the Hamiltonian, we obtain the following equation for the function psi of x. This equation, known as the time-independent Schrödinger equation, holds special significance in quantum mechanics. We will explore this equation and make plenty of use of it later on in this course. So, let's summarize what we've learned. If we find a function psi of x that satisfies the time-independent Schrödinger equation for a specific potential v of x, then multiplying this function by the previously found time-dependent complex exponential gives us a separable solution to the original time-dependent Schrödinger equation. Separable solutions of this type are known as stationary states. We will shortly explore their physical properties and see how they can provide both qualitative and quantitative insights into quantum motion.